Welcome everybody. Thanks so much for taking the time to come to this talk today. It's great to see colleagues from other universities here as well. So thanks for making the effort today. For those of you who don't know, my name's Ollie J. I'm the director of the Heath and Health Research Centre here at the University of Sydney, and really excited about the talk that we have today. So Dr. Chris Trisos and I have known each other for just over a year or so after I visited University of Cape Town for an event that he was hosting, looking at the intersection between climate change and sport. And through those discussions, we've had the pleasure of being able to host Chris on his sabbatical. So he's going to be here until the end of October now. Is that right, Chris? Yeah. So we thought it would be a really good opportunity for him to give us a talk about his background, which is a little different to what a lot of us do in our centre and our wider collaborative group do across Sydney and across Australia. Before I go any further, I just want to acknowledge that this event is taking place on the lands of the Gadigal people of the Eora Nation, and I'd like to pay my respects to elders past, present and emerging. So before I hand over to Chris, I'm just going to give a very quick introduction of who Chris is. So as I mentioned, Chris is at the University of Cape Town. He's the director of the UCT's Climate Risk Lab and the African Synthesis Centre for Climate Change, Environment and Development. And his research is really quite broad. He examines the intersection between climate change, biodiversity, and human well-being. We were having a casual conversation the other day, and Chris just mentioned in passing that he just published another paper in Nature. So he does really, really good stuff, and really looking forward to learning more about it. So without any further ado, over to you, Chris. Thank you.
Thanks, Ollie. No pressure. Hi everyone, thanks so much for taking the time to come to the talk today. Really appreciate it. And I'm going to try and keep things to about 35-40 minutes so we have enough time for questions. And if there's something in the middle of one of the slides that you're just like super confused by, please feel free to ask a quick clarifying question. Thanks to the Heath Health Research Centre and Ollie for hosting me for a sabbatical. It's been really great meeting a lot of people in the group and learning a lot more about human physiology and how we survive and maybe hopefully thrive despite the heat. So I'll be talking about past and near future impacts of climate change. I think the setup for this talk and the kind of background context for me is coming from, I grew up in Cape Town, studied in various places around the world, worked a bit as a practitioner for a year at the World Bank, and then landed up back in Cape Town in 2019. And I think just showing this image, this is the city bowl of Cape Town. It's a very biodiverse area with the national park there, but also just off screen on the left is a large area of informal settlements, and it's a city of extremely high inequality. And so it's both, I think, an important place for a climate lab to be because of really wrestling with a lot of issues of middle income countries around inequality, adaptation, who gets the resources, who doesn't, and what are the kinds of risks we have to deal with in the near future. And one of the things I'll be talking about a lot here in this talk towards the middle part is how do we understand those impacts that are coming sort of next year, 24 months from now, as opposed to 2030s, 2040s, 2050s, the kind of classic projections based on scenarios of future climate risks. And then just to acknowledge a lot of they're not all shown here, but a lot of the members of our team who've done most of the work I'll be presenting today, various lead authors are on these slides. And if you ever want to visit Cape Town, that's we have an annual mini golf tournament that's shown on the left there. So come in the spring. So starting off, I'll be talking about climate change impact attribution. And this slide just goes through a sort of very high level workflow of that, where a lot of you are probably familiar with the detection part, right? And that for a long time dominated the climate impact field. So it's a lot of what I do and a lot of what I think many of you do. So we detect some change of a thing we value, morbidity, human lives, how that's changing in response to climate. But that's kind of a detection of change as opposed to an attribution of is that human-caused climate change that led to that. It could be natural variability in the climate cycles between El Nino and La Nina, different ocean dipoles, things like that. The next step then is attribution. So attributing that detectable change to human-caused climate change. And that's been done increasingly now with rapid attribution. You read about in the news almost in real time when there's a heat wave, like the events that have been happening in Europe. You'll see news headlines a few days later about how much more likely that event is because of climate change. Then we can go an extra step to sources, which is looking at specific emitters and their responsibility for certain changes in hazards, and here I'm going to be going the extra step to impacts. So not just how much more likely was the heat wave because of the emissions of a particular fossil fuel major, but how much more coral bleaching or excess mortality or economic damages are the responsibility of those emitters. And just to give an extra method summary, how we do this in the details, because I won't be presenting in the talk equations for every impact model and things like that. There's really kind of 4 main steps. The first is try and precisely define the impact you care about. Here's an example that might be excess deaths due to extreme heat in Cape Town. The next one is define the hazards and conditions. A lot of studies just use mean monthly temperature. Often we can do better than that. One of the reasons I'm here on sabbatical is to learn for human health in the heat, what are some more precise climate variables and metrics we can use than mean monthly temperature. But maybe mean monthly temperature is a good one, and that's what you've got, so then you go with it. The third one is we understand the climate system well enough and can simulate it well enough in a computer simulation to say, here's the climate we got, and if we remove certain amounts of greenhouse gases, what counterfactual climate would we have seen at a global or regional or local scale, depending on the simulation you run. And then you assess some difference between the world we had and that counterfactual world. Run through, in this case, your impact model. So you might have excess mortality in the world we have and excess mortality in a counterfactual world where no greenhouse gases were emitted since 1850 from fossil fuels. So we did something like that recently to attribute changes in childhood malaria across Africa to human-caused climate change. And this slide, so apologies for the fuzziness, the PDFs weren't this fuzzy. This slide is just showing you the data across Africa. It's about a century of data collected through many health surveys and part of malaria control program efforts. It's about 50,000 observations across many subnational districts. And you can see that over time there have been fluctuations, partly in pink they're linked with periods of sustained malaria eradication efforts. These data going from 1900 up to 2015. So for an infectious disease, it's pretty unprecedented in the time series we have. And that's really nice for climate change impact attribution, because ideally, to really, in some cases, get a nice separation of the trend of human-caused climate change from natural climate variability, having multiple decades of data to get that statistical estimation is a good thing to have. And so when we ran that regression, the main point from this slide essentially is you have this hump-shaped relationship where malaria, the transmission is estimated in this empirical one. The sort of optimum transmission temperature is around 24 and a bit above 24 degrees Celsius. That's quite good to recover from this empirical data because it agrees quite well with lab-based studies of where you might expect transmission to peak. And then on the bottom there's the histogram distribution of the temperatures, mean monthly temperatures across subnational districts in Africa. And you can see a lot of Central and West Africa here sit close to that optimum, even beyond it, and a lot of Southern and East Africa sit just to the left of that. And so what you might expect with climate change is that as these areas warm up, parts of Southern and East Africa are marching up that curve towards more optimal temperatures, and parts of Central and West Africa are going down the curve towards less optimal temperatures. And so a question we were asking then is, how much has this already happened? How much might we have seen that in historical climate change? There are also some flood and drought effects, much noisier. Part of that is precipitation data is much noisier, especially across Africa where we have very sparse observation networks recording precipitation. And then on the right here, and I'll get to this later, this is those two intervention periods in pink, such as the rollback malaria campaign in the early 2000s. And it's showing, which I think is important, that in the case of malaria, when you look at percentage changes in prevalence on the y-axis, the interventions are mostly a much larger impact on malaria prevalence than the climate has been across that time period. So this is a demonstration really of the tools we have to control malaria, at least in the recent historical climate, are sufficient to offset changes that we might see an increase because of climate change. And so here there's I'd say a significant but small signal that you're seeing, and this is averaged across the whole of Africa, so it's hiding a lot of variability. But what you're seeing there in the blue is the historical climate we got as simulated in large computer simulations, and the gray is a confidence envelope from if you hadn't had anthropogenic greenhouse gas emissions since 1850. And you'll see that for most of the time, up until about the 1970s, 1980s, those lines are basically overlapping, and then there's a slight uptick towards the present. But what we really see is where that's important at sub-regional scales. And so this hypothesis of the curve I talked about, Southern and East Africa versus Central and West Africa, is borne out here. The figure labels, unfortunately, are a bit hidden. But what you're seeing on these ones here is the East and Southern African signal, and here's the West African signal, where the observed climates have led to a decrease in prevalence in West Africa, but an increase in prevalence in Eastern and Southern Africa compared to what would have happened without climate change in the gray. And so when we map that across the continent, what you're seeing here in the reds is areas where climate change, human-caused climate change, has led to an increase in childhood malaria prevalence, and in the blues and purples, areas where it's led to a decrease in childhood malaria prevalence over the last century. Again, these are quite small percentage changes in prevalence compared to the impact that control and prevention programs have. And so when we project these into the future, which is something I won't talk about in this talk in that much detail, but projecting it into the future, the hopeful message there is that with sufficient surveillance, secure, like mosquito-secure housing, indoor residual spraying, other malaria control programs, potentially vaccines coming online, there should be sufficient adaptation technology available to more than offset a climate change increase in parts of Southern and East Africa. Nevertheless, there are concerns outside of the climate change arena, such as pullbacks in funding and bilateral and overseas aid for health systems that might mean that's not the future we get, which would be a shame. Because I think what this is saying is, despite climate change, eradication of malaria in the next generations is still possible. A final conclusion that comes out of this work, but related to a systematic review that I was part of, is we need more of these types of attribution studies in the health sector to get a better understanding of the global burden of climate change on disease. Where the few studies that have focused on health have looked has mostly been in high-income countries and heat-related mortality, much less on infectious disease, much less in the global south, and much less on other indirect drivers of health outcomes, for example, looking at the links from climate-induced malnutrition onto health outcomes. And so investment and further effort in this research field, I think, is an important thing for better understanding the impacts that human-caused climate change is having on us at the moment. Moving to the source attribution part of the talk, and this is just a quick primer in coral bleaching. Like Ollie said, my background actually as an ecologist in biodiversity research, so a lot of our lab kind of sandboxes and tests ideas in the biodiversity space and then goes out into other sectors. Some work we've been doing is around but-for causality, which is a legal principle that gets applied in tort law, and it's basically like, would the damages to thing X have happened but for the actions of, in this case, a particular emitter? And so if you answer that like, yes, they would have happened even if the defendant did that thing, then you don't have the case there. But if it's like, no, this damage would not have occurred without the emissions of specific emitter X or Y, then you've got causal standing. And so what you're seeing here in the red is the changes over time in the percentage of sites around the world, coral reef sites that had more than 10% of that site coral bleached under particular El Nino events, especially is when this peaks. In the black line there is all greenhouse gas emissions, fossil fuel land use change removed. And in the blue line is this but-for case of we've removed the emissions of the top 10 largest carbon emitting companies. So those are groups such as Gazprom, ExxonMobil, Chevron, large carbon emitters, Saudi Aramco. And the but-for part is the difference between that blue and the red line there. So but for the emissions of the blue, you would not have had that additional damage to coral reefs in that gap. And so when you do that you can do this hundreds or thousands of times, removing specific emitters. What I'm showing you here is territorial emissions of countries. So that's for Australia there, it's not including your fossil fuel exports, it's the territorial CO2 emissions that happen domestically on the land of Australia. And this is then the responsibility associated with those 4 site-level coral bleaching events. And so what you can see, corals are kind of a canary in the coal mine, special case here, where it's, if you take all anthropogenic emissions to date, it's virtually certain that virtually all of the coral reef bleaching we've seen since the 1980s is because of human-caused climate change. And then unsurprisingly, when you break that down into individual groups, the largest historical emitters, such as the USA, the EU group of countries, and the UK and China, have the largest responsibility there. And then we put in these other countries like Indonesia, Australia, because they host large, important coral reef biodiversity areas within their territorial waters. And so Australia and Indonesia, they sit at about 7% of coral reef bleaching events can be linked to the territorial emissions of those countries. And then you can look at inequalities as well. So on the left, what you're seeing here is regions that have, at the bottom, no socioeconomic dependence on coral reefs, and at the top, high socioeconomic dependence. So that might be on the bottom, somewhere like a landlocked country in Europe, or somewhere in Europe that has no reefs in its overseas territories, for example, Hungary perhaps. And on the top, you've got high socioeconomic dependence places like the Maldives. And what you're seeing on the left is that same thing, but the pattern's reversed, and that's because countries with no socioeconomic dependence on reefs have done most of the greenhouse gas emitting, causing most of the coral bleaching, but most of that coral bleaching has happened in countries with small amounts of greenhouse gas emissions that have high dependence on coral reefs, like small island states. So this starts to get at a climate justice question around where are the emissions happening and where are the impacts happening. And so now these are some preliminary results. The rest of the talk is all stuff that's in progress. So it could be subject to change, and a lot of these results have only happened in the last sort of couple of months while I've been here, a lot thanks to members of my lab who are working in different parts of the world on these problems. And so we're asking this question, but for heat mortality in South Africa. And so this is South African mortality data from 2008 up to 2025. You can see there's strong seasonal signal with a declining trend on it. A lot of that declining trend in the 2000s is from the introduction of antiretrovirals with the HIV epidemic in South Africa, and then a COVID spike. And on the right here, you can see the distribution of temperatures across subnational districts, mean daily temperatures in South Africa. So most days are sitting at around 20 degrees Celsius for most districts in South Africa. But this hot tail up here is what we're interested in because that's what drives the heat mortality impacts. And this is a curve that Tussel Mondoa, a PhD student in our lab, put this together recently. And so this is an econometric causal estimation where we put in a bunch of effects for things like day of year and district to control for other unobserved factors that might drive mortality, such as income levels and local policies, things that could vary through time or across space, be different district to district. And when you do that, you recover a temperature mortality curve that's similar to those that have been published for many other regions, with this steep climb with heat and then a gentle but sustained climb with cold temperatures. The next step then was to try and get a little more sophisticated, and this is still very preliminary stuff, looking at how humidity interacts with that, where we see that at higher humidity levels, the red line there, that curve climbs more steeply than it does at lower humidity levels, the blue. And this is something we're still working on. I think we could possibly do better with our metrics here, getting from daily to hourly levels to get a better understanding of when the maximum temperature occurred with a particular humidity value. These are averaged over days, so still very preliminary. But when you run that through one of these attribution pipelines, what you see is that South Africa, since 2008 up until now, has had about 120,000 mortality events attributable to the hot side of that curve, so that's extreme hot days, and about 100,000 fewer cold attributable mortality events. And if you put that on the map for South Africa, where are those excess heat deaths occurring? It's occurring in the northern areas, north and northeast of South Africa. The north there, up this area is like the Kalahari, extremely hot, dry, and up in the northeast, also very hot. Too hot season, often it's hot around October, November, and then again you'll get heat in February, and more humid in those areas. And the more high elevation center of the country in the cooler south coast, where we have currents coming up from the Antarctic, many fewer excess heat deaths. That's where you would see the avoided cold deaths. And so when you look at these together and do that by country emissions analysis, you see again, unsurprisingly, largest historical emitters, where we can portion out for China, the United States, and in this case, including South Africa. So the emissions, territorial emissions of South Africa have led to approximately 2,200 heat attributable deaths happening in South Africa since 2008. And then we can do this looking at fossil fuel majors, carbon majors. Some of the switches here for things like former Soviet Union to Gazprom are with the transition in Russia from out of the Soviet Union into the Russian Federation. So different analyses group those differently, but essentially many of the carbon majors responsible for several thousand heat attributable deaths. This avoided deaths thing here, I think, gets to an interesting question and discussion in parts of the climate attribution literature and more public discourse, where people will say, oh, maybe climate change is a good thing. It's saving Africans from cold mortality. And this is, I think, where we really have to have a more nuanced discussion around causality and how we communicate some of these things, because you could also view some of those deaths. This is all cold-related deaths. It's not just direct cold exposure, right? Our analysis doesn't get to that. But in a country that has many people living in energy poverty, many people living exposed to extreme cold or heat, there are other layers you could put on top of this for kind of more multi-causal analysis. And it also depends on the forum in which you're voicing this, right? Depending on the local legal context and people's rights, saying, oh, I caused 3,000 heat deaths, but I saved 2,000 other people, so actually it's not that bad. That's not kind of the way we do things from an ethics perspective, right? This next part is not attribution. It's some of our more preliminary stuff, but hoping to move it towards the attribution space. And that's learning and playing in the heat of climate change. And so some work we've done here with a collaborator in the US using data from Chile on school progress through school and entrance into university is starting to show some interesting and potentially concerning results, where what you're seeing here in these different colors is the impact of temperature on someone going through school and reaching grade 12, then going on to enter a tertiary education institution, what they call there a selective university, which would be a kind of top-tier research university, or a high-earning degrees, some professional degrees such as legal, engineering, medicine, etc. And out on the right-hand side here, you can see that the more days you have above 27 Celsius during your high school career, the lower chance you have, or it has a negative impact on your chance of being in a highly selective university or getting into a tertiary degree. So again, a lot more robust checks that need to be done here, but quick surveys of the climate and education literature. It's quite interesting. There are a lot of studies that seem to center around somewhere between 26 and 27 Celsius outdoor temperature as where you get the onset of detrimental effects on learning, whether that's exam scores or more standardized testing over longer periods of time. And this is one of the longest periods of time in that literature, and that tracking students all the way through a high school education. This is some work with a collaborator at University of Chicago, and also with input from Ollie and the group, using some of their metrics around low, medium, and high risk for playing particular sports. This is just a map for football, showing, compared to a mid-century average around the 1950s, how many additional days of the year have at least a couple of hours disrupted in that high-risk category for outdoor playing of football. And for me, we can turn this into an attribution study. I think we possibly will. One of the more interesting questions, though, that I think hasn't been answered in in maybe as comprehensive a way as it could be, is planning throughout the kind of school day for learners. So like what's happening with the heat in terms of your learning outcomes in the classroom, how does that interact with the physical exercise you can take in lunch break or after school, how does that link with extracurriculars? Do you have to think about, like some schools are already doing this, right? Restructuring the whole school day around when is it cool enough to exercise outside versus learn optimally? And when might you shift your exam schedules? For example, South Africa writes a lot of exams just before the summer holidays, where parts of our country are increasingly exposed to extreme heat days at the moment where someone's writing their school leaving exam that helps determine their university entrance. Should we be thinking about moving that earlier in the year into a cooler season? So what do we learn from this impact and impacts attribution? Well, we learn a lot about loss and damage from human-caused climate change. We also learn something about where we're not adapted to the current climate and the climate as it's changed. And then it has uses in particular legal contexts around liability. But the second part of the talk now is really sort of what about foresight? And what can we adapt to in the near future? And here's an example of the heat waves context for just school heat wave days by global warming level, the proportion of that. So these are days above 27 Celsius or various other metrics, and how they will increase in proportion in a world of global warming 4 compared to a 1970 to 1990 baseline. So even by 1.5, parts of the tropics there are having just under half of the days of the school year are hot days. And forecasting risk for climate and health, sort of a lot of work to date has thought about these long-term risks. You could make the same map for biodiversity, for crops, for certain infrastructure. There are hundreds of these studies, and the IPCC does a good job of synthesizing them every 5 to 7 years and making confidence statements around risk. And then there's a whole forecasting community at different time steps. And I'm giving a climate and health example here where we're quite used to, in some high resource countries, having weather-related health information communicated to us, or certainly in agriculture this happens. And that's typically up to 2 weeks. And then maybe 3 days out or a week out, you get a heat wave health warning or a tropical storm warning, and your local government might take certain actions and recommend people find a cooling center or evacuate or things like that. Then we have seasonal forecasts. Often this is for infectious disease. What you're seeing on the bottom here is dengue forecasting, and that kind of has a 3-month look ahead, maybe 6-month look ahead. And then you get into the space of long-term projection, which is under a particular scenario of greenhouse gas emissions, how much of the land area would be suitable for transmission for a particular infectious disease. Again, this is dengue in 2050 or in a very high emission scenario, showing how the expansion of transmission. But a geographic map of an exposure or a hazard is quite different from a risk and an impact that incorporates vulnerability, exposure, the hazard, has been well controlled for a causal link of climate on an impact. And so the question we're asking is, how can we really fill this missing middle, which is 1 year to 10 years in the future, right? It's not a long-term scenario projection on greenhouse gases, but it's further ahead than a seasonal forecast can give you information on. And so this is still very preliminary work in our group, where we're trying to just initially ask the question, how skillful can we be taking the impact models, some of them from the attribution work we've done, and using some of the latest climate science. Again, here, apologies, but you can get the general message from these figures. On the left is temperature, and what you're seeing there in the red and the yellow is places where a particular climate prediction system, and the key element in these cases is initialized with current climate observations, as opposed to a historical run, which would have been initialized maybe with climate observations of 100 years ago, and by the time it gets to the present, chaos in the climate system the trend is there, but whether the El Nino happens in that historical run in 2027 or 2030 is determined by the internal variability of that simulation, as opposed to initializing the simulation, say, this November with the current sea and atmospheric states of the world, and then your model is more in synchrony with that natural variability in the climate. And so while it's still imposing a warming trend, it's hopefully also getting El Nino and La Nina cycles and other things closer to correct with what will happen in the real world. The crosses here show where that initialization approach, which requires quite a lot of computing power to run these large ensembles, is not doing any better than if you just average the climate and say, what I expect next year is the average of the last 10 or 30 years. But for temperature, you can see a lot of that doesn't have crosses, and so over a lot of the tropics, a lot of the land area, you do have skill from this approach. For precipitation, it's not showing up that clearly, but basically almost the entire land surface has those X's. So there's very low predictability looking even a year or 2 years into the future for precipitation. So we're focusing mostly on heat-related impacts for this type of work. This is some, again, building from biodiversity and going into other sectors. Some work a postdoc in our group, Andreas Meyer, is doing, trying to predict, will next year have a record-breaking heat event compared to the historical baseline experienced by particular species. This slide is for about 7,000 species of amphibians, and showing we have some predictable skill in this, looking at will there be a month in the next year, just a 1 year look ahead, will there be a month in the next year where a species in a given place will experience hotter temperatures than it's seen before. That's not quite an impact forecast because we don't know if those hotter temperatures would lead to population decline. It's more exposure, but it's our initial testing of it. And what you can see on this slide in gray is the era 5, so the reanalysis data that's kind of close to truth. And in red there, or orange, is this decadal predictions, the 1 year, 5 year look ahead. And so, as you'd expect, what you see in year 1 is quite a close match between the 1 year prediction and the era 5 data, and that's the extra skill being given by initializing that climate model with observations of what the climate is like at that particular time. But then it starts to drift. And so by forecast year 5, you're not doing that much better than the blue line at the bottom, which is just a historical climate simulation that was ignorant of how it was initialized compared to the current climate, right? And so really, this is showing, as we might expect, we've got more forecast skill year 1, maybe year 2 still useful, depending on your decision-making needs. And we're extending this with some machine learning work, another postdoc in the group looking at how well we might be able to predict things like maize yield in the US 1 year into the future, and then transfer that learning into other lower income contexts such as tropical agriculture, where there's higher climate skill potentially because of El Nino having a stronger signal on interannual temperature cycles in those regions, but the maize yield data, for example, is much more uncertain in those areas, so building an impact model is harder. So often there aren't that many places where you have both the really good climate data and the really good impact data to merge them outside of high income country contexts. And then one thing I'm interested in doing while I'm here is trying to extend this into getting a little more understanding of, can we predict not just something like excess mortality with this kind of system, but actually for a particular group, for elderly people or for elderly people with hypertension. And so this is going back to those temperature and mortality curves I showed you earlier for South Africa, and sort of disaggregating that humidity impact by age group, showing it's really in the older age group that you start to see this humidity effect play out. So if you were going to do a 1 or 2 year forecast ahead and talk to a local health agency, you could get more specific and say what things might be put in place now, because we're leaning towards a summer that might have record-breaking heat, that might have a particular case number for elderly people. And so what might you do if you have a 1 or 2 month warning as opposed to an 8-day warning, or a 1 or 2 year warning as opposed to an 8-day warning? Last bit of the talk is some work we're doing on adaptation services. This is kind of building on climate services, which a lot of us are familiar with. You get increasingly good communication about the hazards, the heat waves, the droughts, the floods. Adaptation services trying to take this the next step about, like, okay, what works for adaptation? What's effective? What's feasible based on the hazard prediction? And then transfer that evidence across contexts. And so this is part of something called the Global Adaptation Mapping Initiative, which happened with the last IPCC cycle. And it was just a very large, hundreds of collaborative coders, kind of people donating their time to look through all of those studies with blue dots on that map, and extract the adaptation relevant information and try and code how effective and how feasible they were. It was largely successful as a snapshot in time of what does the research literature say about who's adapting where. And what we're trying to do with the current work, which has just started and been funded, which I'm very happy to share, is use a lot more AI-enabled coding and data aggregation in this, and then also have much more co-design with policymakers. The first one was really kind of to serve an IPCC chapter. The idea with version 2 is that it'll be a continuously living database where we can go back to not just the academic literature, but also project reports from organizations like the World Bank or the Green Climate Fund, and regularly update the information. Who's adapting? How are they adapting? Is that being effective by certain measures? And what kind of resourcing was required to reach that effectiveness? And ideally then, a far future version of this might link that with particular impact predictions or other risks that people think are salient, so that it's useful and searchable in that kind of way, so that you can get a library of adaptation options that may be effective in your context. And I'll end there. Thank you so much.
So do we have any initial questions that anybody wants to ask? Because I've got a few that I can kick us off with, but shall I do that? And then you can gather your thoughts and we'll go from there. Just if we go back to the early slides, Chris, by the way, thank you for that wonderful presentation. That was brilliant. I'm interested in the malaria optimal temperature question, and how that then interacts with optimal temperature for people. And so I guess the concern is that you've got this warming which would reduce the suitability for malaria or for mosquitoes that carry malaria, but it also reduces the suitability for people as well. And I suppose in most places people are pretty fixed, but is there any evidence that there's mobility within these areas whereby in the settings where the temperatures are getting so high that they're bad for malaria, but they're also no good for people as well? So people actually move through behavior and through mobility, are moving more to the places where malaria is still suitable.
Yeah.
Does that make sense?
That's a good question. I don't know anyone who's looked at that specifically in the malaria context. We didn't, but there is a growing literature on climate mobility, which is quite complicated around who moves and who stays. Often it's those with more resources and family connections elsewhere that are able to move first. There have been some projections done by, I think his name is Alex Deschevenen at Columbia University, using large-scale kind of climate land use models around how much internal migration you might expect in African countries with different climate hazards. One of the things in the malaria context, and this is kind of hypothesis from me, but a risk factor that some people will be worrying about is if climate change accelerates aspects of rural to urban migration, and new mosquito vectors from Asia, for example, coming into Africa that are more able to persist in urban areas at higher temperatures, then with more of your population in those urban areas, you could increase risk of mosquito-borne diseases that way.
You got an increased exposure, basically, there.
Yeah.
And so with those data that you showed, there was population wasn't overlaid into that, is that right? Or was
it's just a prevalence rate, so it's kind of per 100,000 people.
Okay, so
It's not like a case number.
Okay. Have we got any burning questions from anyone? Yes, please. I'll give you the.
Thank you. I just have a question around, this is very, I have a personal interest in this area rather than I know anything much about it. But I was interested in the research about heat, temperature, but I was also wondering about things like UV exposure, because just anecdotally, normally through winter here, the UV levels are a lot lower, but I've noticed that they're kind of going up. I was just wondering if you know anything about that, or has anyone looked into that?
I'm not an expert on UV and cloud cover, other than to say, to the extent that cloud cover in some places is an important moderator of that, it's one of the things that global climate models struggle to simulate the most, because a lot of cloud formation and dissipation happens at grid boxes like spatial scales much smaller than the grid box of a climate model. So you could, in theory, run a climate model at like centimeter scale resolution, but then to run it for several years in terms of computing time would just be massive. So we run them at larger grid boxes and then have equations that like parameterize what clouds are doing. But yeah, one of the outstanding questions in climate science is not necessarily better understanding cloud microphysics, but better representing that to understand what will happen to clouds as the climate warms, and then how that lets more sunlight in or not in different parts of the world. Yeah.
Interesting.
Sorry, I'm just going to... Might I just refer back to a conversation that you and I had a few weeks ago, the one about the albedo effect of clouds themselves and how that's potentially threatened by climate change. Can you maybe just describe that in a bit more detail as well?
So there has been some research using simulations of much smaller extents, so not on the whole planet. And I'm not fully up to date with this in the last year, but basically machine learning assisted climate models and also process-based climate models where as you warm, you get collapse of certain things like stratocumulus cloud decks that are prevalent in some parts of the world, like over parts of the tropics, that are pretty persistent there and reflect a lot of sunlight back to space. And so with the collapse of those cloud bands, you then have more incoming sunlight and you can get, it's a feedback loop that leads to more warming. The same as melting of large areas of ice leads to more warming as it reflects less light back. So that is something that is a sort of potential tipping point in parts of the physical climate literature that people are worried about.
And the interaction between clouds and ice sheets is particularly concerning, isn't it?
I don't know enough to say if it is or not. Yeah.
Okay, all right, no worries. Do we have any other questions? Do you want to follow up? Or? All right, maybe I'll just go follow up and then we'll go to Fazana.
Well, just quickly, I was just on a practical level, because I just wonder about things that will make people act, I guess. But if skin cancer rates, for example, if there was, not in the climate models, but if you could actually see with more hotter weather, I'm not using the right lingo, but more UV exposure for kids at school, or it would also show up in other data possibly as well. But not knowing anything about it.
I mean, I think my only quick sort of adjacent response to that is there's a lot of commentary at the moment, right, about like, will the heat waves that are happening in the northern hemisphere summer at the moment lead to a moment of action? I think very much to be seen, right? Like, we've had unprecedented heat-breaking years, several of them in the last decade, and wildfire. If you think of the wildfires that happened in Los Angeles not so long ago, and it depends on a whole lot of factors, how quickly they're either like normalized or used to spur action, or both, right?
Yeah, I think on that point, I think there's that discourse around what's been happening in Europe this northern hemisphere summer, and people are becoming or waking up to the fact that Europe is heating up at a double the rate or the average rate, and whether that will then spur people into more action. Just with respect to your skin cancer comments, there was some encouraging news this morning that I saw, is that there's a new trial which was really positive about treatment for skin cancer. So there's good news sometimes as well as bad news. So, Fazana, do you want to ask your question?
Hi, Chris. Thank you for presenting these interesting pieces of work that you are doing. I was really interested on the school attainment piece, the work you're doing with the raising temperature, how the chances of getting to higher education is getting less. So I was really interested to know the pathways, like which are the factors that you were thinking that can contribute relating to heat. Is it like absenteeism, where there are more heat days, students are attending the school less, or is it like the heat or cognitive development of the people?
Sure. The short answer is the way that model's currently built, it could be all of those things. So it's not built to identify a particular causal mechanism. It's built to identify in a way we're confident is a real effect, a relationship between temperature and leaving high school and then entering tertiary education. And there's quite a rich literature and increasingly emerging, and many people, I think, writing really good reviews on those kinds of pathways and how those things might play out. But yeah, it can be a variety of factors. It can be, this was only looking at days during someone's high school, so it's not if they were exposed to heat, for example, as a 1 or a 2-year-old, and how that might affect cognition, but it's more things like it might relate to absenteeism, it might relate to drowsiness and discomfort in the classroom and people paying less attention. It might relate to lower teacher performance on hot days. There could be a whole bunch of things happening there.
So on that note, I might hand the mic over to Shamila, who's one of our colleagues who holds a Horizon Fellowship, who is really quite interested in this area of educational outcomes and heat stress. Shamila, over to you.
Thank you. Thank you so much, Chris, for the wonderful talk. I have actually 2 questions related to the schooling and educational outcome. In your slide, you showed a trend towards 27 degrees Celsius. I would like to know your insights above that threshold. What will happen between 27 to 30 and above 30 degrees? Did you have any observations in African school-based or educational data? And my second question is, in your follow-up slide, you showed a global map of, I think, heat wave, I think school day heat wave, and how that impacts different regions around the world. Did you look at school hours data globally? Is there any database available to look at different parts of the world, and I mean, those are school hours data, excluding holidays and out of school hours?
Yeah, on the above 27 Celsius, I would also love to know the answer to that question. That data was from Chile, where there aren't, we try to estimate that at about 30 and 33, and the confidence intervals just blow up because there's not that many observations once you go above 30. We are starting to work on some South Africa data this month, which we don't have as much information there on university entry, but we do have the ability to follow people from grade 8 through grade 12 and test scores. And so there, I think we'll get closer to 30, but how much above 30, I'm also not sure, because of the high elevation parts of South Africa and the south coast also don't often see days that hot. So yeah, I think it's an open question. We did do some re-estimation with authors who were kind enough to share data from some of the other education outcomes and temperature stuff, and the results above 30 bounced around a lot. Like, I think the reason a lot of studies are seeing an onset around 26, 27 could be something real, but then they're not really specifying how the curve changes after that. And I think a lot of it is just like low sample size, and the estimates really get unruly. On the map of school heatwave days, the way that was done was from the UNICEF Giga project, which mapped school locations as part of an effort to get broadband internet into schools around the world, or get schools connected. So there's several million school locations. Maybe about 30 or 40% of the world's schools have a pin in that data set. And then we had a research assistant who went to all sorts of different sources, looking at like, when is exam calendar, when are the holidays in different districts of different countries, and it's there. It's imperfect. There will be, like, if anyone zooms in at a sub-district, there are some uncertainties in exactly the holiday days, also because we've done it over several decades and some of those have shifted. But I think it's pretty robust in terms of removing holiday days, removing weekends, and the assumption was the average global school day goes from 8 a.m. to 3 p.m. I mean, that's also not the case everywhere, but we had to kind of, just to make the analysis computationally feasible, have some kind of rough estimate of when people are at school.
Perfect. Thank you so much.
Thank you, Shamila. Okay, so I'm just going to go around here. Do we have any other questions from anyone particularly? Yeah, well, please, over to you.
Hi, Chris. Thanks for the nice presentation. I'm one epidemiologist, so I'm very glad to see you have shown this U-shaped curve in South Africa data. More also interested in the malaria. So based on your mortality data, do you have like individual level data? Can you look at the malaria or other infectious disease? Does this climate change or the heat also impact those mortality for the infectious disease in particular?
So South Africa does have quite good mortality data. Ollie and I were actually on a call with people from the South African Medical Research Council. There's uncertainty about how good the individual level underlying cause of mortality data is. So that's something we're still trying to work on in the next few weeks. So I could get back to you, but to be discussed further. Yeah.
Any other questions? No, okay. Well, I might just finish off with two more quick ones, if you don't mind.
Yeah.
One is about emissions. So I was really interested in that figure that you demonstrated of who is responsible for what emissions. And there's obviously the US that was, well, not obviously, but the US was leading. And then a close second was the EU. But there's really quite different levels of uptake in renewables between the EU and the United States. So I was just wondering if we had that graph plotted 20 years ago, or maybe it is, I can't remember exactly what the time scale is, were the EU leading and now they're dropping below the US because of a greater uptake in renewables? And if so, is that cause for optimism?
Yeah. I don't know if they'd be leading 20 or 30 years ago. It'd be interesting to do that. But I expect, you would see some in that analysis. Yeah. Some of that, well, there are two things going on there. So the source attribution stuff is both how much you've emitted, but also when you emitted it.
Yep.
So once CO2 is well mixed in the atmosphere, it stays up there for centuries and heats the planet for a long time after you emitted it. And so country blocks or countries that started emitting a long time ago thus bear more responsibility than someone who started emitting like yesterday, right? Sure. And especially that for coral reefs where we're already at a level of global warming where we're seeing widespread damage. Yeah. If you come along and do a lot of emissions after something is locally extinct, then
you can't extinct
are you responsible for the
yeah.
So I don't know. I expect that gap might be less if you did it 20 years ago. And many EU countries are certainly decarbonizing more than sub-regions of the US.
Sure. Yeah, and there are parts of the US that do have this transition going on as well, right? Which is to be celebrated. Probably the last question I'll quickly ask is something that I've wrestled with a bit over the past few years, is this constant counter-argument of climate change with respect to heat-related deaths and cold-related deaths. And so I really appreciated the data that you presented there. What you also presented was the classic temperature mortality relationship, the curve, which is a U-shaped curve. I just wondered if what your thoughts are on how that offset, if you want to call it that, between cold-related deaths and heat-related deaths, even though it's already demonstrating that there are more heat-related deaths relative to the cold-related ones. As we move into the future, what's really evidence from those temperature mortality curves is that the hot end is a lot steeper. Yeah. And so, and it's shallower than the cold-related end. So while that offset is going to become increasingly disproportionate, presumably, just wondered if you wanted to comment on that, whether that's a correct interpretation and what we might expect.
I think for a lot of places, I think that discussion around how much has climate change saved people or caused excess death in the temperature space, maybe I have some patience for it in the historical stuff, but going into the future, I think it lacks, it exists in its own somewhat like climate justice and fact devoid bubble. Yeah. Which is unhelpful because it just assumes that our approach is like the world stays as it is, which it shouldn't. Yeah. We should help people adapt on both ends of that curve, right? I don't think it's necessarily say, let's celebrate that climate change has saved all these people from cold deaths and then it's also killed more people from heat deaths. It's like, no, there's energy poverty on the cold side that also prevents cooling on the hot side. With better rollout of renewables and local climate justice initiatives and better resourcing, you can just deal with the whole problem.
Let's make it zero on both sides.
Yeah, exactly. Instead of say have the emissions helped save more people than they've I think that's, it quickly can get into the discourse of delay of why we shouldn't act faster on climate change. It's not all bad. And then that's just kind of freezing how the rest of society should respond to climate risks, right? And then your second point is a largely valid one. For most of the world, where most of the people live, that curve climbs steeply, and as it warms, you will see increasing like deaths on the hot side.
Yeah. Great. Okay, so we're at the hour now, or the half hour. So could you just finish off by giving a round of applause to Chris, and thank you very much.